The second last dot point that we need to deal with for topic 4.1 special relativity is about the mass-energy equivalence. Now, we've actually covered this before back in Unit 1 when we looked at nuclear physics, dealing with binding energy and energy released due to nuclear fission, nuclear fusion and radiation. So it might seem a bit unusual to bring it up again here. The reason why we are is because it actually comes from special relativity. Now, to deal with this scenario, we're going to consider what happens when we accelerate an object, and it's probably going to be easier here to think of that object as being something like a proton, so something small that we can easily accelerate to speeds that are quite fast. So we've been able to achieve that in the Large Hadron Collider. In order to get the object to move at near the speed of light, we must actually do work on it. In the Large Hadron Collider, the work's done by electric fields as it accelerates protons by applying an electrostatic force to those protons. So we can go to the equation that we've seen there before, being W is equal to Fs as our starting point. Now obviously that's Newtonian physics, so we need to work this a little bit further to get to a stage where we can apply some relativistic physics. So we're going to use Newton's second law and then identify that acceleration there is actually given by a change in velocity over change in time. So now we're starting to get to this aspect of velocity. Notice in the top there we've got a mass times a velocity, so we can say that force is actually equal to the rate of change of momentum. So we can make that substitution for the force and say that the work is equal to the change in momentum over the change in time multiplied by the displacement over which that change in momentum occurs. Now hopefully you can recall from Unit 2 that when you do work on something, you're actually transferring energy to it. So work and energy are effectively the same thing, just seen from different perspectives. Work is what you would do on the system, and energy is what the system gains due to you having done work on it. So the work done results in the object gaining kinetic energy in this particular scenario. So we can again just make a direct substitution there, and instead of writing W, we can write that there's a gain in kinetic energy due to that work being done, which is equal to the rate of change of momentum multiplied by the displacement. So we're now set up to a stage where we can do something with this equation, and that something involves some mathematical steps that are a little bit above what we need to cover in this course. So these steps are not something that you need to be particularly worried about. If you do want to look it up, you can always go and consult some other sources and make sense of the steps, so the integration by parts. The other thing we're going to also do here, as I said, is make sure we're incorporating relativistic physics, and we're going to do that by considering relativistic momentum. So as I said, there's a few potentially confusing steps in that process, so I'm going to skip over them and just show you what the result is. And that result is that EK can be expressed as m0 c squared over the square root of 1 minus v squared on c squared minus E0. So that's the end point of that particular calculation, and that value E0, when you go through and do an integration, you'll always end up with a constant term at the end of it, and in this case that constant term is the rest energy of the object. So we have that interesting scenario for kinetic energy, but what does it really mean? If we consider the kinetic energy when the velocity is 0, that means that we're going to have EK being equal to 0. So if we make those substitutions, we end up with 0 is equal to m0 c squared over the square root of 1 minus 0 squared, so 1 minus 0 over c squared, minus that term E0. Now hopefully you can see here that this term of 1 minus 0 over c squared, this term is effectively going to disappear, and so we're left with 0 is equal to m0 c squared, given that we've divided by the square root of 1, and that's subtract E naught at the end still. So we then have this relationship that E naught, the rest energy, is equal to m naught c squared. So you can see there that we've now arrived at the mass energy equivalence. The important thing to note about this equation is that usually you'd sort of talk about mass being converted to energy, but a more appropriate way of thinking about it is that mass and energy are just different versions of the same thing. So it's not so much that mass gets converted to energy or energy gets converted to mass, it's more that they are just different expressions of the same quantity. Now the version of this equation that you'll find in the data booklet is slightly different, and we can just look at the changes of these things. So I'm just going to notate here what the data booklet version is, and that's delta E being equal to delta M c squared. So same sort of idea as the line above, but just note the difference there in the representation in the data booklet. Now if you look back at the equation for kinetic energy, you might look at that and think, well, how do we get the Newtonian version of that, being Ek equals half mv squared, out of that mess of an equation? So I want to just explain that quickly. It's not something that you really need to worry about in terms of the syllabus, but it will help to just confirm that all of these concepts that we're dealing with are effectively one type of physics, and all of the Newtonian physics that we're dealing with are just special cases associated with special relativity. So if we look at the situation where V is much, much less than C, I'll just rewrite that equation again. So Ek being equal to m naught c squared on the square root of 1 minus V squared on C squared. And I'll use the expression for E naught being m naught c squared here. So we're going to apply a few mathematical tricks here to simplify this equation a bit. And the first is that we're just going to rewrite this as 1 minus V squared on C squared to the power of negative a half. And we're still going to have minus m naught c squared. Now we can use the binomial approximation here. And again, as I said, some maths here that you might not have covered before, so you might have to take some of this as a given, or if you're interested you can go and have a look at where this idea comes from. So the binomial approximation can be summarized as saying that if you have an expression 1 plus x to the power of a, that's approximately equal to 1 plus ax. So it just simplifies that expression a little. Under certain conditions, those conditions being when the magnitude of x is less than 1 and the magnitude of a times x is much, much less than 1. And in the case of v being much, much less than c, then both of those conditions are met. So what we can then do is write that Ek is equal to m naught c squared outside of 1 plus a half V squared on C squared. If you're interested in looking even further, those two terms are the first two terms of the Taylor series expansion, and the rest of the Taylor series can be ignored because the values of those other terms become insignificant. The next term would be v to the power of 4 over c to the power of 4. So if v is much smaller than c, then that term can be ignored. If we take that expression now and expand it, we'll have that Ek is equal to m naught c squared plus 1/2 of m naught c squared multiplied by v squared over c squared minus m naught c squared. Now you'll notice here that we've got m naught c squared at the front and m naught c squared at the back. We're subtracting that term, so those two terms are going to cancel each other out, and we also have c squared over c squared, and so what we're left with is our Newtonian physics version of this equation. Ek is equal to half mv squared. So you can see there that Newtonian physics is basically just a special case of relativistic physics where the speeds that we're dealing with are significantly slower than the speed of light.